Acharya garu. Sir.
Sir, please go ahead, sir.
Start chedama.
Yes, sir. Sir, go ahead, sir.
Good evening to all participants. On the occasion of 103 birthday celebrations of Dr. Komarval Chandrasekharan Garu, our department is conducting a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. Yesterday, Dr. N. Sudhakar Garu, Professor, Department of Computer Science and Engineering, Bapatla Engineering College, Bapatla, delivered a talk on machine learning models. Approximately 717 participants attended for yesterday's session. Thank you one and all for your kind cooperation for your yesterday's session. Now I request our head of the department, Bapatla Engineering College, Dr. KVLN Acharya Garu, to address the gathering for today's session.
So, dear esteemed faculty members, good evening to all. We are all gathered here through virtual mode in the second day of our International Faculty Development Program on applications of mathematics in various fields with innovative approaches. We all know that applications of mathematics with the conceptual approaches definitely enrich the faculty members for enhancing their knowledge in multifarious fields. In addition to it, it also helps us to update existing knowledge in teaching community and create a deeper interest in various fields of mathematics. Yesterday, the first session was enriched with a valuable lecture by our eminent Professor Dr. N. Sudhakar Garu on machine learning models. I am thankful to all of you for your active participation and interest towards enhancing your knowledge. Today, our resource person is Dr. KNVV Varaprasad Garu from Department of Mathematics, Guru Gaisadas Viswavidyalaya, a Central University, Bilaspur. Sir, any problem? Sir, any problem?
From my end, there is no problem.
Sir, now it audible?
Yes.
Sir, can you hear my voice?
Yes, sir. Audible, sir. Audible.
Okay, thank you, sir. Sorry for the inconvenience. Dear esteemed faculty members, good evening to all. We are all gathered here through virtual mode in the second day of our international faculty development program on applications of mathematics in various fields of, okay, with innovative approaches. So we all know that applications of mathematics with conceptual approaches definitely enrich the faculty members for enhancing their knowledge in multifarious fields. In addition to it, it also helps us to update existing knowledge in teaching community and create a deeper interest in various fields of mathematics. Yesterday, the first session was enriched with the valuable lecture by our eminent Professor Dr. N. Sudhakar Garu on machine learning models. I am thankful to all of you for your active participation and interest towards enhancing your knowledge. Today, our research person is Dr. K.N.V.V. Varaprasad Garu from Department of Mathematics, Guru Ghasidas Vishwavidyalaya, a Central University, Bilaspur. He did commendable research on functional analysis under the able guidance of Professor G.V.R. Babu Garu from Andhra University. I am sure that his ability not only captivated our attention, but also deepened our understanding of functional analysis and its application. Definitely, his knowledge has to show significant impact on us. Hence, I feel privileged to have such a good resource person today with us in this section. Sir, thank you very much, sir, for accepting our invitation. Finally, I appreciate all our participants for their continued enthusiasm and dedication to stay with us throughout the session. I am sure that today's session will be a fruitful one with a learning experience with enjoyable and enlightening. Thank you one and all. Thank you very much.
Thank you very much, sir, for your valuable message. Today is the second day in the 5-day International Faculty Development Program. Today's speaker is Dr. K.N.V.V. Varaprasad Garu, Assistant Professor, Department of Mathematics, Guru Ghasidas Vishwavidyalaya, a Central University, Bilaspur. Now I request one of our staff organizers, Ms. I. Rajeswari, to present profound profile of Dr. K.N.V.V. Varaprasad Garu.
Rajeshwari madam, we are unable to hear your voice. Please unmute your voice, please. Okay, madam. Now we can hear. Please go ahead.
Two students have obtained PhD and two are pursuing their PhD under the guidance of Dr. Varaprasad Garu. He completed one project sponsored by UGC of worth 6 lakhs rupees. He delivered invited talks in various national and international conferences. He is a life member in various mathematical societies. Presently, Dr. Varaprasad Garu is working in the area of nonlinear analysis, fixed point theory, and applications. Dr. Varaprasad sir is prized by one and all for his best way of teaching from the last 3 decades. His soft nature, motivational behavior, teaching abilities, research capabilities, and additional strengths to him apart from his goodness and vast experience in the field of education and research.
Thank you, Rajeshwari, for your nice introduction about KNVV Varaprasad Garu. Now I hand over the session to Dr. KNVV Varaprasad Garu.
Okay, sir. Thank you very much, Karnaka sir and Srinivas sir. Nice introducing me, Rajeshwari madam. Encouragements. First of all, I would like to thank my Guru, Dr. P.V. Ravindranath Babu Garu. Because of his guidance, I am here in front of you. And also, thank you very much for giving this opportunity for express my research area and interesting also. And this is a 5-day international faculty development program on applications of mathematics in various fields with innovative approaches. Title is a very interesting title. And also, according to this title, also in my research area, I'm taking one of the important particular area, that is discontinuity points and fixed points. Discontinuity at fixed points, I chose it. And at present, in this non-linear analysis, in particularly fixed point theory, this area is also a very emerging research area. Very few people are doing in this area only. A few people only doing research. Some and also very good applications is possible from here. I am also working right now. We are working in applications area also, especially for the neural networks and some other biological modeling problems also. I am working on it now. So in this regard, this title is attracting to me. Immediately I chose it this one. I accepted this invitation, and interestingly, I would like to put it to this, especially discontinuity at fixed points. I would like to give a lecture on this topic. So, according to Rajeshwari madam, nice introducing me, and also I would like to give my short number also. My title of the talk is that on the problem of discontinuity at fixed point. This is the first of all the my title, and the second is that we'd like to go basic facts and introduction. I would like to give the basic facts. So first of all, I would like to give the from basic onwards. Later on, I'm going to be go for the particular area what I'm going to be give lecture. So right from beginning, we'd like to give a fixed point definition. That is the, let us take it X is a non-empty set and T is a self map on X. And we can take it X is belongs to X is called a fixed point if it is satisfies Tx is equal to X. And immediately it is easy to identify that. So some mappings may be just a single fixed point, some mappings may just more than single, some mappings not having a fixed point, some mappings have an infinite fixed points. I would like to provide some examples also. See this example. See this example, very easy to identify that. I'm giving a sum of examples only here. This is the example in if we are going to be observed, because we are particularly going to be go for the very particular area. Before going to be enter that area, I would like to give a basic concepts and with examples. So therefore, dear students, dear participants, is this voice is clear, sir? Yes, sir.
Sir, it is very clear, sir. Please carry
Thank
on.
you.
Sir.
Thank you. So therefore, from basic convert, I like to take it example x is equal to x square plus 5x plus 4, and especially
So I request all the participants, please unmute your audio. Please, this is humble
Yes,
request from the organizers. Except the presenter, I request all the participants, please unmute your mute your audio, because it is creating some disturbance for us. Please consider it. Sir, please, sir, go ahead, sir.
Thank you very much, audience and dear audience. So this is the f of t, that is the notation, that is the collection of the all fixed points of t. And if we are taking f of t is equal to in particular minus 2 is the one of the only number. If you are taking then this part, this is the example that is that x square minus x, tx is equal to x square minus x. In this function, we are going to be find out f of t is equal to 0 to 2. And third one is that dx is equal to x plus 2. There is no fixed points in this case. And tx equal to x. This is, of course, it is called an identity mapping. Every point is also an interior point. Actually, these are examples easy to solve. In general simplification model, we will be getting. Some problems may exist, we cannot solve that problems. Therefore, for finding of a fixed points, so we are going to be use the nonlinear analysis, especially in the Banach fixed point theorem onwards. It will be useful. Applying the theorem statement, if it is holds the conditions respect to theorem conditions, then we can say that that problem has a fixed point or not, whatever. So in this regard, first of all, go for the first is one of the important theorem, famous theorem, that is the Banach fixed point theorem. Before going to be give a Banach's theorem statement, I would like to give a iteration sequence. That is, let x be a non-empty set. One is a non-empty set, x be any set, and t is a self map on x. Take it any point on x. We are going to be write it inductively. We are going to write t naught of x is equal to x, t power n plus 1 of x is equal to t of t power n of x. And in this case, we are going to be write it. The sequence is like this: xn is equal to 2xn minus 1. That we also can write it t power n of x naught, n is equal to 1, 2, 3, 4 up to so on. In fact, such type of iterations is also used in our community, especially numerical analysis, iterative methods, iterative methods and Newton-Raphson methods. Such things also, some methods are also there. That is the taking the initial point. We are going to be creating a sequence concept. This particularly this xn is equal to txn minus 1 is called, that is a sequence of successive approximation with the initial value x naught. This particularly we are going to be called Picard iteration, starting from the any initial value in that the provided space. From here onwards, there is another way in the, especially in the nonlinear analysis, approximation theory. The generalization of the Picard iteration is the Mann iteration, and after that is a Ishikawa iteration, Noor iteration, and the entire in that section there is another type of a research. I'm not going in that way because my intention is wanted to say that discontinuity, at what is the nature of a discontinuity condition at particularly at the fixed point. So before going to be taking that problem, go for that. This is the important definition, a very well-known definition for everyone. So this is, let us take it x to be a metric space, and t is self map on metric space xd, and we are going to be write it. This is the d of tx ty is less than or equal to d of xy, and we are going to be write it. This is the this is called a Lipschitz condition. Lipschitz condition, that means a capital L is greater than or equal to 0 also. If it is equal to 0, what happens? This is d of tx ty equal to 0. T going to be right, that is the constant mapping. So therefore, I avoided equality condition. Only I'm going to be take it L greater than 0. L is a positive. If L is equal to 0, definitely T, the given mapping T, forced to be constant mapping. That is the constant mapping. In particularly, there is a sub cases is possible. If you are taking it in this highlighted inequality, if we are choosing an L is equal to 1, then this inequality we are going to be notation as denoted as the non-expansive mapping. And if L is particularly less than 1, 0 less than, L less than 1, that means L, capital L is a lies between 0 to 1, then we are going to be write it, that is the contraction. And T is a contractive also if d of tx ty is less than d of xy for all x, y, and x. This is the primary. Everyone is also learned earlier also. This is also useful to us also. So now come to the point of the very famous theorem. This is the Banach's theorem. Simply, I would like to write it in simple form. let T be a self-mapping on a complete metric space. That means we are going to be taking a space is a complete metric space. And T satisfying the condition, D of Tx dy less than or equal to H times of H times of D of xy. And H is lies between the semi-interval 0 to 1 for any x minus x. Then definitely T has a fixed point, unique fixed point in X. T has actually it is a typographical mistake. T has a unique fixed point in X. And proof I'm not to be given because there is a skeleton of the proof I would like to give in the skeleton part. First of all, we are going, one of the ways is that we are going to be construct the sequence with using of the Picard iteration and find out whether it is a find out that was a decreasing sequence. After that, whether it is converges to 0 or not, we are going to be found that we have to show that the sequence is a Cauchy. After that, you are going to be show that whether it is a has a fixed point or not. And finally, it is easy to verify and giving the provided inequality, it is a uniqueness. This is the Banach contraction after elevating of this Banach fixed point theorem. Then very vast of applications is also rises, and it is also useful, and Banach fixed point theorem is very useful, and several applications is solved with using of this one. But it is the one of the important part is that if any application is also is satisfying this complete metric space, I mean Banach fixed point theorem, then definitely that solution equation has a unique solution. And particularly if we are talking about the Banach contraction principle, here T is a force to be continuous. Actually, T is a force to be continuous. Therefore, Banach contraction principle, actually that is only for the applicable if mapping is a continuous only. Then one question is arises, if T is not continuous, what happens? Is it possible to say that whether that equation has a fixed point or not? So then question is arises. So that means if only a Banach contraction principle is applicable if equation has a fixed point, I mean continuous only. So in this question, immediately that question is arises, and one question is arises, that is do the edges some contractive conditions do not force the mapping T to be continuous. In this regard, in 1968, Indian mathematician Kannan answered this question affirmatively and proved a fixed point theorem following contractive conditions. So what is the contractive condition? This is the Kannan's mapping theorem. This is the let TBS self-mapping on a complete metric space X, and T satisfying the contraction condition. Condition is that this is the condition d of Tx dy is less than or equal to h times of d of x dx plus d of y dy by 2. And this h is lies between the semi-interval 0 to 1 by 2. Then T has a fixed point. So in this function, that means definitely if T is discontinuous, here T is discontinuous, then it is easy to apply if it satisfies the Kannan theorem statement. Definitely T has a unique fixed point in. Immediately after published of this particular theorem, energy published in the same theorem also in the different notation. That is the statement is that complete metric space XD and T is satisfying conditions. In particular, I am not mentioned in particularly in this slide. So I would like to explain here. In particular, this is the here it is.
మొదట్లో వచ్చేసారు కదా మళ్ళీ
అది ఏమైంది సార్ నాకు అర్థం కాల
కొంచెం వాయిస్ స్లో అయింది మ్యూట్ అయింది
D of Tx minus
యూట్యూబ్ కదా సార్
యూట్యూబ్ గారు
D of X dy plus d of ytx. But Chatterjee is taking the inequality same, but it is the distance in the right hand side is also is mentioned. It is a xty and y d of ytx. Then it is replaced and it is also satisfying the conditions. Is also same conditions and the space is the complete metric space. And if it is satisfying the same hypothesis, then T has a fixed point. So therefore, Kannan is the first is giving a one affirmative answer. T need not be a continuous. Then we will give a answers about this. So after that also with the Chatterjee, concluding of Banach and Kannan and Chatterjee, there is a one question is arises here is Jamfirescu in 1972, and Jamfirescu is introduced the following contract to condition. This is this condition. The statement of this Jamfirescu is very interesting. That is the condition. What is the statement is that let us take it that is a TBS self map on a complete metric space, and if T satisfies at least any one of the conditions. T satisfies at least any one of the conditions, that means of d of xy or d of txy less than or equal to Kannan condition or Chatterjee condition, then T has a unique fixed point in X. This is the this one. Now I would like to go for the back. Go for the back. So this is happens here. One question is arises in the after Banach fixed point theorem, that is that T is a forced to be continuous. Is it possible if T is a discontinuous or not? Kannan is given. So the variation of generalization of the Banach contraction principle is possible of two spaces is happens here. That is what is the one by weakening the contractive properties of the map and by extending the structure of the ambient spaces. In my talk present, I would like to use these two conditions. I would like to change the space and I would like to change the contractive properties in my particularly chosen area. That is the discontinuity at a fixed point. So therefore, this is these two things I'm going to be using here. And this one is Kannan condition. Already I explained it. And Kannan is supposed this one is that Kannan fixed point theorem gave rise to the famous question of continuity of contractive mappings at their fixed points. Particularly at their fixed points is not he posed this question also, but there is no answer is given still 2019 and 19. It may be observed that Kannan contractive condition does not require the continuity of the mapping T for the existence of fixed point. However, T satisfying the Kannan contractive condition turns out to be continuous at the fixed point. And after that, first I would like to give a few only contract inequalities which is generalized part. Already earlier also I mentioned it the previous slides. This one in this slide actually this slide I would like to explain a few weakening the properties of contractive properties of the weakening के what is that? This is the Kannan. This is the condition is a weaker than of the Banach contraction. No. In 1971, Reich introduced the following contractive condition. The register non-negative numbers A, B, C is belonging to the semi-interval 0 to 1, and A plus B plus C. C actually 2 is not there. It is a typographical mistake. This is not don't be considered. This is less than 1. For any x, y, and x, d of tx, ty less than or equal to a times of d of xy plus b times of d of x dx plus c times of d of y ty. After that, in 1972, LJB Sirik, he is a mechanical engineer, but his contribution is in mathematics is a very high. Sirik introduced the following contract to condition. There is just a non-negative numbers ABC is in semi-interval 0 to 1, A plus B plus C is less than 1, and for any x, y, and x, and this condition going to be hold. Actually, This should be is here, and top one should be is here, and here it is a plus b plus c plus 2e less than 1 here. These two is a sum of I'm presenting only these two sum inequalities only. After that also several inequalities also generalized out of this one. After that there is another direction. Banach contraction principle he generalized in the 1969 Meir-Killer. Meir-Killer is also generalized Banach contraction principle in a different direction. That direction is called epsilon delta contraction. It is a very famous direction, and also little bit of difficulty also for understanding. I am also used in the final my result in this contraction also. So in 1960, what happens in Meir-Killer's condition up to 1968-69 is generalized in the what I presented in the previous inequalities that is the mentioned earlier. In 1969, Meir-Killer is published a paper that is published a fixed point theorem, which is a remarkable generalization of the Banach contraction principle. In that condition that is mentioned here, a self-map T is called a weakly uniformly strictly contractive. In fact, that is the very famous as a epsilon delta contraction. What is the epsilon delta contraction? That is that for any epsilon positive, there is a delta positive such that epsilon less than or equal to d of xy less than epsilon plus delta implies d of tx less than epsilon. That means RHS, this is actually originally d of tx less than or equal to d of xy. It is mentioned in Banach contraction principle. Therefore, epsilon is less than or equal to right hand side term less than epsilon plus delta implies left hand side term less than epsilon. Actually, this is the generalization part. If T satisfies the Meir-Killer contraction, then automatically T is a contractive condition. So if you are applying here, that is the d of txy less than epsilon, and that should be is a less than d of xy. So if you are concluded of this one, you will be get very easy to understand that t of tx ty is less than d of xy. Already I mentioned it in first 2-3 slides when I explained the Lipschitz contraction condition. I mentioned the d of tx ty is less than d of xy. That is the contractive condition. After that, actually, Meir-Killer published the paper. There is several mathematicians shows their interest and developed this Meir-Killer condition in different conditions. I would like to a glance look. I would like to give a glance visible. I mean presentation here. Only brief presentation I would like to give what happens in the Meir-Killer conditions presentations. See this one. This is the originally Meir-Killer's definitions theorem statement. The theorem statement is already explained. Once again, I would like to read it out. Let XT be a complete metric space and T be a Meir-Killer contraction, and that is the Meir-Killer contraction. Then automatically, then T has a fixed point. I mentioned it. That is something already mentioned. So I'm not read it out. So if T is satisfies Meir-Killer contraction, then T has a fixed point. Originally, this condition is famous as a Meir-Killer contraction. So after that, in 1992, Chekaminsky is collected and published one research paper. It was published in Journal of Mathematical Analysis in the Applications, and he compared up to the 1992. He compared some Meir-Killer conditions in their presentation. What is the relations and the possibility applications? They mentioned it. Actually, these information is also very useful to us. What I am going to be explained to the discontinuity at a fixed point. So for giving a main result in the discontinuity at a fixed point, these things are prerequisites area. One is the Banach contraction principle. What is the when it will be problem is posed from the Banach contraction principle, and I used a Meir-Killer condition also. Therefore, I would like to give a Meir-Killer conditions history After that, I used in my main theorem is a two mappings. Between the two mappings, I used some definitions, and also I changed the space also. Therefore, I would like to give a new space also. I would like to. Therefore, before going to be enter my main result, I would like to present what I needed prerequisites areas. This is the Jakamesky is mentioned it particularly. So what is Jakamesky's presentation? I collected it in an aggregate. I would like to mention it this one, and this is the A I dash A I and double dash B I C I. So therefore, for any epsilon positive, there is just a delta positive such that for any xy and x, ai is mentioned like this: epsilon less than or equal to mi of xy. What is the mi of xy means that? So in next slide, you can understand that this is the RHS right hand side term of the inequality. I means I is equal to 1, 2, 3, 4, 5. That means m1 of xy, m2 of xy, m3 of xy, m4 of xy, m5. What is m1? What is m2? What is m3? What is m4? I mentioned it in later. In the next slides, I mentioned it. Therefore, this is a relation. I would like to take a blind observation. I would like to see this one. Epsilon is less than or equal to of the RHS term, epsilon plus delta, d of txy less than or equal to less than epsilon. And here it is the both sides, it is a 0, and this is the 0 less than, and this is the conditions. Therefore, a1 ai dash, ai double dash, bi and ci in up to 92, 1969 Mercalli is introduced. In up to the 1992, this much of result, I mean this much of research is done from the great mathematicians. I collected it such things, I mentioned it, here it is. So what is the m1? What is the m1 means that is the m1 of xy is equal to d of xy. m1 of xy is equal to, suppose let us take it first of all, m1 of xy is equal to d of xy. Please be remember it. I would like to go for the one slide back. So this is so one side back. This is, let us take it to this one. If I is equal to 1, m1 of xy, that is equal to d of xy is less than epsilon plus delta d of x. Therefore, in place of this one, if you mentioned it d of xy, definitely ai, that means a1 is called a Mercalli contraction. Please be understand that is the language what I'm going to be mentioned here. If you are taking a1, that means I is equal to 1. That means a1. A1 means that epsilon less than or equal to m1 of xy less than epsilon plus delta implies d of txty. That means m1 of xy means that is the d of xy. Therefore, a1 is called indirectly, that is called Mercalli contraction, like this. Therefore, I would like to go for the next one is that this is what is the m2 inequality is mentioned like this. M2 of xy, that is the maximum of xtx and maximum of yty, and M3 is that it was d of xy and d of xtx, d of yty. M4, that means of xy, xtx, y of ty, f of xty, ytx by 2. M5, maximum of xy, d of xtx, yty, xty, ytx. These 5 inequalities are very famous. Those who introduced, I mentioned it in the next slide also, it is easy to identify. In particular, my talk, please we remember, it was adjusted in the slide number 18. At the end of the talk, I'm going to be recalled from 18th page. So next that we observe, A1 is okay. Observation A1. A1 means that is the originally that is a Mercalli contraction. A3 means that I is equal to 3. If you are taking the main equality previous slide, therefore it was called Maitipals. It is introduced. A4, that is a park and roads they introduced. B1 is considered Matakowski and Vezerese is also introduced. And also they proved in that paper A1 and B1 are equivalent. I'm due to time, space, time duration and space duration. I'm not providing that proof also. It was mentioned in especially Jakamski's paper. This is a very nice paper. Those who wants to do research in especially in the mere-killer contraction. So some observations I collected from that Jakamski's paper. Jakamski's paper, that is the I is equal to 1, 2, 3, 4. Condition A1, AI is equivalent to A dash, and I is equal to 1, 3, 4, 5 condition AI dash is equivalent to AI double dash. A2 double dash is implies that A2 dash, but these are converses not true. And A1 implies A3, it is implies A4, this is implies A5. And A2 double dash is implies A3. These are a blind proof is also available in the Jakamski's paper, and it is not possible to here it is a presentation, and my intention is a different. Therefore, I collected this information, wanted to share to our loving participants. So now in the another direction, I would like to go for the another direction. That means if any theorems contains more than one mapping, there is some definitions are needed, avoiding the continuity part also. For avoiding of continuity part, we need to introduce some important definitions. Important definitions is needed. That important definitions I mentioned it here. It is important definitions is this one. So this is, let us take it first of all, understanding of this definition, very most important. Suppose let us take it in XD is a metric space. XD is a metric space, and F and G are two self maps, and one is a commuting. Commuting is a simple definition. Everybody knows that. That is the FGX is equal to GFX. If it is a satisfies this condition for all any X and is in a main domain, therefore you can say that the pair of mapping FG is a commuting. So, and weakly commuting, this is the slight generalization of the weakly commuting. This is the condition is mentioned here. That is mentioned, it is this one, and it was introduced in a CESA in 1982. He introduced weakly commuting. After that, very vast research is going on. That is the after commuting, that means of commuting implies the weakly commuting, and weakly commuting does not implies the commuting. After that is the junk. The junk is introduced, junk and roads is introduced compatible mappings. This is the very most important and famous definition, especially in the complete metric space in the fixed point theory research area. And compatible. What is the compatible? That means of limit n tends to infinity, FGXN, GFXN tends to 0. Whenever xn is a sequence in a given domain and such that fxn and gxn converges to the same limit for some t in x. Suppose if it happens, definitely that a pair of mapping is called that is a compatibility. So what is the non-compatibility? Especially non-compatibility is also very famous. This is I used especially in the later action. So non-compatibility means that, so it is not a compatible. Compatible means that the upper line, it is not necessary it converges to 0. That means maybe it is a neither non-zero, otherwise non-adjust. If it happens, then you can say that compatibility is not a compatible, that is called non-compatible. Non-compatible definition is that if there is at least one sequence, if you found any one of the sequence in X, fxn and gxn tends to T for some T in X, and then the limit n tends to infinity d of fgxn, gfxn is either non-zero or non-existent. Non-existence. Non-existence. If it happens, this is then we can say that that pair is called non-compatibility. And next, after that, in 2000, before that, 2000, before 2000, it is a little bit orthography. Here is a mistaken here. Occasional weakly compatible. I forgot the weakly compatible. Yes, it is weakly compatible. Okay. So Junk and Rhodes in 1998 they introduced weakly compatible. That weakly compatible is definition is that the two pair of maps is two pair of maps satisfying the commuting at their coincidence point only. So that means that the mapping commute at their coincidence, but that we can write it as fgx is equal to gfx whenever fx is equal to gx. After that, actually, after that weakly compatible, we need to explain the occasionally weakly compatible. First of all, I would like to explain the occasionally weakly compatible in the next place it was mentioned. Before going to that, I would like to mention this is the property satisfying EA property. That means if there is a point, there is just a sequence xn such that limit n tends to infinity fxn is equal to limit n tends to infinity gxn is tends to t. If it is only holds, no other conditions, then we can say that that is the property EA. So therefore, after that, occasionally weakly compatible. This occasionally weakly compatible is a generalization of the weakly compatible definition. What is the definition is that fgx and gfx is a commuted to their coincidence point, not for the all, for some only. The difference between the weakly compatible and occasionally weakly compatible is the only ones. Weakly compatible definition is that commute at their coincidence points only. Occasionally weakly compatible means that commute at their some of the coincidence points only, not for all coincidence points. Therefore, weakly compatible definition is implies that occasionally weakly compatible, but converse is need not be true. After that, Junk and H.K. Pathak is introduced biased maps. It is a very famous published paper in the Proceedings of American Mathematical Society, biased maps. What is the biased maps? That means that G is a G biased. Fg is a self-mapping. We are calling that is a G biased. G biased means that whenever xn is a sequence in X and fgxn, fxn, gxn tends to t in X, then alpha times d of fgxn gxn less than or equal to alpha times d of fgxn fxn. What that means is sometimes if f is equal to limit infimum, otherwise alpha is equal to limit supreme. These are definitions of some important definitions here. After that, in the same paper, after that, in the same paper is also he introduced the G bias maps of type A and F bias maps of type A also. After that also, and Pathak and Vijay Cho and SM Kang, he introduced bias maps of type A, G biased and F biased maps of type A. What is the definition of this one I mentioned here? I would like to read it out. If whenever xn is a sequence, whenever xn is a sequence in x and x and fxn and gxn tends to t in x, alpha times d of gtxn fxn less than or equal to alpha times d of fgxn gxn and alpha times d of ffxn gxn less than or equal to alpha times d of gfxn fxn, where alpha is equal to limit infimum, otherwise and alpha is equal to limit supremum. This is the definitions, and I would like to give a one conclusion. The relations between these things is mentioned here. Commutativity, the relations between the above definitions, I'm going to be mentioned the shortcut manner. Commutative, that implies that a weekly commuting, and every weekly commuting need not be satisfying a commutativity condition, and weekly commuting implies that compatible. Compatible implies that compatible, weekly compatible. Weekly compatible implies that OWC that is mentioned, that is occasionally weekly compatible, and it implies that biased maps, and it implies that biased maps of type A. Actually, I'm not mentioned in the slide. There is a there is a I would like to explain here. Compatible conditions in the parallel, there is a independent definition is also mentioned. Compatible maps of type A means weekly computing implies compatible maps of type A also. But compatible and compatible maps of type A both are independent. It is clear from the literature. Now come to our personal talk. What is this talk? I mean, in this my talk, in this my talk, actually, post one open question. What is that open question? That means that on the existence of contractor definition, which is strong enough to generate a fixed point, but which does not force the map is continuous at the fixed point. So after Banach contraction, T should be is a continuous, and Kannan is relaxed with the continuity definition, need not be a continuous, then it will be true. That means in that theorem also, T is a continuous at fixed point. That means T is a of course, mapping is not a continuous. Mapping is a discontinuous, but that discontinuity point not at a fixed point. That discontinuity is then another point, but T is a fixed point of T only. Now, according to B. Rods, is posed one question: is this possible? Mapping is a discontinuity at particularly fixed point. That means a discontinuity at fixed point. This is, I am touching this area. Therefore, we are developed, and RP Pant is give a affirmative answer after a long time, and after that also in this area research is also going very slowly, and a very few people are doing in this area, because and also some neural networks, some modeling problems is also possible to solve this problem in this area. Now this is coming to the point here, how Pant is solved this problem. This is the in 1999 up to 1999. The problem B. Rose posed a problem that is only simply pending. That is a problem. In 1999, Pant is proved this open problem is in the following. I mentioned what I am presenting in screen. See that one is what is that? Pant proved the following fixed point theorem, obtained the first result that intermediate discontinuity at the fixed point. And the proof is also very interesting proof also. Especially, we are going to be show in that proof also, we are going to be show T should be discontinuity, particularly in the fixed point. At the end of this talk, I'm going to be show how we are going to be proving T, particularly T should be is a discontinuity, especially in the fixed point. First of all, we are finding a fixed point, and we are trying to show T should be is a discontinuity, how it will be. So in Pant is mentioned the technique. In this paper, it was published in Journal of Mathematical Analysis and Applications in 1999. Let T be a self-mapping on a complete metric space, and T satisfies the condition d of tx dy less than or equal to phi of maximum of d of x dx, d of y dy for all x, y, and x. And also second condition, that is the for a given epsilon positive, there is a delta of epsilon is greater than 0 such that epsilon less than a maximum of d of x dx, d of y dy less than epsilon plus delta implies a d of tx dy less than or equal to epsilon. Then t has a fixed point, you can say that is the z. So that is the z only. So in this particularly we used, this is the M2. Or you remember it, this is the 18th slide, it is mentioned it is M2. And also one controlling function is also introduced, because we are not given the controlling functions importance in these slides. That will be a different type of concept, also altering distance functions. Therefore I would like to give, this is the controlling function. What the controlling, what is the phi conditions is that I mentioned here. This is the phi is a mapping from r plus to r plus, is a mapping satisfying the conditions phi of t is less than t for all t positive. This is the condition, and this is the condition. Then t has a unique fixed point in z. It is simple, and he mentioned it. Moreover, t is a continuous at z. T is a continuous at z. T is a continuous at z if and only if limit extends to z, maximum of x dx, maximum of x dx, d of x dx, d of y dy is equal to 0. This is the most important. That means if it is not equal to 0, that means t is not a continuous, t is a discontinuous. If t is discontinuous, then it cannot be false. That means the last line we are going to be rewrite it in the different way. T is a discontinuous at z if and only if limit extends to z, maximum of d of x dx, d of y dy is not equal to 0. Not equal to 0. If you proved it, then definitely it is a t is a discontinuous, and t is a discontinuous at particularly z. Already z is mentioned as a fixed point. So therefore he in this paper he very interestingly he proved it. This part is a very interesting proof is given. T is continuous at z if and only if limit extends to z, maximum of d of x dx, d of y dy is equal to 0. So actually this is the after publishing of this theorem, and he extended also. He extended up to the 2 mappings also he extended. The proof I am not given because I generalized these results also. In that theorem I mentioned it proof also. And after that there is a one latest approximately recently it was published in 2017. Bishop and Pant. It is also published in Journal of Mathematical Applied General Topology paper. This is we give some more solutions to be open question, existence of contrary definition, which are strong enough to generate a fixed point, but which do not force the mapping to be continuous at the fixed point. So what is this one is that Bishop and Pant is mentioned here. So he changed the inequality. He generalized, that means of change this one changed this inequality, that is the m of xy, that is m of x. So what is the m of xy? I mentioned it at the end also. I mentioned it in last. This is the m of xy. Please you may easily you can understand that is the t is the self mapping and a complete metric space xd, and t square. T square is a continuous. T is not a continuous. T square is a continuous here. T square is a continuous and satisfying the conditions. First condition, as it is in the previous slide, d of tx dy less than or equal to 5 times of m of xy. And second condition is that for a given epsilon positive, there is a delta greater than 0 such that epsilon less than maximum of m of xy. Of course, here it is, I mentioned it, maximum is twice, it is not necessary here. Is a typographical error. This is the epsilon less than m of xy less than epsilon plus delta implies that d of tx dy less than or equal to epsilon. Then t has the unique fixed point. You can say this is the z. Automatically t power n of x is equal to z. And he is also mentioned directly T is a discontinuous at Z if and only if limit extends to Z, and M of E, this is also not necessary, M of xz is not equal to 0. Of course, this last line is also, we can write it as in the previous slide. In the previous slide, I would like to show, this is the previous slide. Here it is mentioned T is continuous Z if and only if limit extends to Z, M of maximum of d of x dx, d of y dy is equal to 0. And the same definition, same technique also they used in the discontinuity manner. That means T is a discontinuous at Z if and only if extends to Z, maximum of M of x Z is not equal to 0. This is the mention. And also, I created a one example also. Of course, Bishop and Pant is also mentioned in the different example. I'm also giving a one example also. Let us take it x is 0 to 2. X is equal to 0 to 2. It is a complete metric. And D is a usual metric if you are taking. If your T is a self of an X, if you are observing this one, that is a Tx is equal to 1 if X is equal to 1, and T is a image is 0 if X different from 1. Definitely what happens, this is 1 is a fixed point and T is a discontinuity at 1. T is a discontinuity 1 also. I mentioned it here also in the next line. T satisfies the all conditions of the above theorem and has a unique fixed point x is equal to 1, and also T is a discontinuity at 1. That means T is a discontinuity at fixed point 1 also. And also it is satisfying the all conditions. The first condition is satisfying if you are choosing a phi of T is equal to T greater than 1, phi of T is equal to T is T by 2 for T is equal to 1. And T is satisfies the condition 2 also if you are choosing this is the delta of epsilon is equal to 1 for epsilon is equal to 1. In this, actually what happens, this is the delta of epsilon, means this is the dependent value of the epsilon. If you are taking an epsilon, according to that epsilon, we are going to be get a delta of epsilon. Therefore, I am going to be find out if you are taking an epsilon is equal to 1, we can find out delta of epsilon is equal to 1. If you are taking an epsilon is less than 1, then delta of epsilon is a sufficient 1 minus epsilon. If you are taking this one example, it is easy to find out and easy to solve it also. And also it is easy to find out in the limit, if your x tends to 1, the m of x1 is equal not equal to 0, then automatically then T is a discontinuity at 1. Of course, 1 is a fixed point, therefore T is a discontinuity at a fixed point 1. So after that, before coming to the my main result, so I would like to give a concept of the B matrix space. Please. Someone is raised a hand. Okay. Otherwise, please, after completion of this talk, we will give a time also, 15 or 20 minutes time. In that time also, I will give a answers to you, whatever you posing the questions. So meanwhile, please write it on your paper and keep it after completion. Then definitely we will provide in time, and you can ask at the time also. Now come to the point here, the concept of the metric space, that is the B metric space. It was recently in 1993, it was introduced by Hizrevich. This is actually this B metric space is a generalization of metric space. Of course, he is provided a weaker conditions, especially for the triangular inequality in the metric space. We know the metric definition. First is a non-negative, second is symmetry, and triangular inequality. And in the B metric spaces, he weakened the conditions of the triangular inequality. and formally it is defined as a B-metric space with your generalization of Banach contraction principle. And Kesrevic is also proved with using of the B-metric space Banach contraction principles also. That means Banach contraction principle is also still valid in B-metric space. After that, also several spaces are also introduced: B-metric space, partial autometric space, and the extended B-metric space, and several metric spaces is also introduced, and research is also going in very vast. I would like to give a definition in the B-metric space here. That is the I would like to read it out. Please see this one. Let X be a non-empty set, and small s is greater than or equal to 1, be a given real number. Given real number, a function D is mapping from x cross x tends to R plus is called a B-metric on X. If you are taking n for any x, y, z in X, the following conditions are false. That is the three conditions: d of xy is equal to 0 if and only if x is equal to 0, d of xy is equal to d of yx, and d of xz is less than or equal to s times d of xz plus d of z. That means if you are taking an s is equal to 1, automatically B metric space is reduced to the metric space. B metric space is reduced to the B metric space. So that means that if you are taking a s is equal to 1, this is s greater than or equal to 1. This is the s less than or greater than or equal to. If you are taking in here, it is s equal to 1. Nothing. You can remove it. S is equal to 1. The d of x y. Actually, this is a typographical mistake. Here it is not x z. This is sorry. It is correct. X z is less than or equal to the s times s is equal to 1. If you are taking, automatically this is called a triangular inequality. Therefore, B metric space is reduced to the metric space. If S is more than 1, if S is more than 1, then it is not a metric space. It is the B metric space. That means we have some examples also which is satisfying the B metric space but not a metric space. That means especially everybody knows that those who are teaching in the metric space, modulus of x minus y whole square, modulus of x minus y whole square is not a metric space. That means it is a metric space. There is several examples is also there. In this talk also, I mentioned it in some examples also. This is the B metric space definition. B metric space definition. In this B metric space definition, before going to go for the important of some needful informations, I would like to give a topological concepts also. In the B metric space, we are going to be create B metric space. Suppose Cauchy sequence. The definition of Cauchy sequence in B metric space. The definition of Cauchy sequence in B metric space. That means suppose unfortunately I am not mentioned in this slide, but I would like to say to you a sequence. Suppose let us take it xn is a sequence in X. That means for each epsilon positive, generally what is the metric space? Metric space in the metric space d of for each epsilon positive, there is just a n naught in n such that d of xn xm is less than epsilon for all nm greater than or equal to n naught. Same definition also it is applicable in especially in B metric space also. And also the convergent sequence, the convergent part is also that. That means there is just a L is suppose let us take is a L is a convergent value of the sequence. That means there is a L is belongs to the given space such that for each epsilon positive there is a del n naught is belongs to n such that d of xn L less than epsilon for all n greater than or equal to n naught. So suppose a B metric space is said to be complete if every Cauchy sequence is convergent in it. Same definitions also, same topological definitions as this we are going to be take it. So only importance is that as importance only we are going to be give. And every B metric space is a metric space. Every B metric space is a metric space, but metric space cannot be a B metric space. Some examples also we provided in that. In my main concept, in my main talk, that is, I need these two importance. I given importance of these definitions arbitrarily continuous. P.S. Chaudhary sir is also one of the mathematicians in Calcutta, and he's also introduced some developed and weaker conditions also he introduced also on arbitrarily continuous. The definition is a very simple. If a self-mapping on a metric space XD of the set order of XF is equal to F4n and is equal to 0, 1, 2, 3 up to so on n is called a orbit of F. Is called orbit of F at a particular point X, and F is called arbitrarily continuous. This is arbitrarily continuous, and U is equal to limit infimum. Limit F for mi of X is equal to m plus Fu is equal to limit I tends to infinity F power F of F power mi. If it like this, then you can say that that is the arbitrarily continuous. And the second definition is weakly arbitrarily continuous. If is a self-map on metric space XD is called weakly arbitrarily continuous, and if it is satisfies this condition. So, dear participants, give a 1 minute, few seconds. I come back with water, take it the water, and come back within few seconds. Thank you very much, and sorry for the disturbance, inconvenience to you. This is two things. Now I entered in the my main results. Now this is my main result. So this is my main result is that that a TBS self-map on a complete TBN self-map on complete B metric space. That means I changed the space, B metric space. XD such that D of XY, D of TX dy, maximum of D of XY and D of XTX, D of YTY, and 1 times of 1 by 2 times of S, 1 by 2S times of D of XTY and D of YTX. And also the second condition for given epsilon positive, there is a delta positive such that epsilon less than or equal to M of XY less than epsilon delta, and implies that D of TX dy less than epsilon. This is the mere killer condition. This is the M of XY means that this right hand term, entire term, I'm mentioning as a M of XY. That I'm mentioning M as XY. That means epsilon is less than or equal to, or RHS term is less than epsilon plus delta, implies that D of TX dy less than epsilon. This is. Then if I consider this one, because I consider these two parts actually, if you are taking an S is equal to 1, then this theorem is also valid in directly metric space. If you are taking a S is equal to more than 1, it is valid in the B metric space. And also this is the conditions, and the complete metric space, B metric space is a metric space, complete metric space, but the reverse is not happens. This is the conclusion of this theorem is that T possesses a fixed point in X. T is I'm going to be taking it T is a weakly arbitrarily continuous. That means I'm not taking T is directly continuous. If T is a arbitrarily continuous, automatically T has a fixed point. This is my conclusion. Finally, moreover, the fixed point of T is unique and T is continuous automatically if and only if the right hand side term is going to be tends to 0. That means that This is also, this is so this part is also this part is also, we can write it, we can treat it, that is a T is a discontinuous, T is a discontinuous at the fixed point of T if and only if limit extends to Z, M of xy is not equal to 0. I am going to be give a proof after the end of the, after presenting of the second theorem also. After that, you can understand that the beauty of the proof is that general part is a very easy, very similar manner. Then the general part for showing of a fixed point of T with using of the provided hypothesis is a general way. That means a traditional way we are going to be prove it. But the beauty of that, T should be discontinuous at fixed point. T is discontinuous at a fixed point. That means indirectly we are going to be show that the highlighted part is not equal to 0. If highlighted part not equal to 0, that means T should be discontinuous. That is the beauty to showing in the proof. This is the main theorem, and I extended my main theorem in the following way. So I extended the following, then that means I mentioned it. This is the two mappings. I'm taking the two mappings, that is F and G be non-compatible self mappings. I'm taking is a non-compatible. I already mentioned in the previous slides, just 20 minutes before, non-compatibility. What is the non-compatibility? I would like to explain now that once again I would like to explain non-compatibility. That is the F and G both should be, F and G both should be is a there is a one sequence needed to there is for any sequence xn. There is a sequence in xn in x such that fxn gxn tends to t for t is a sum in x. That means d of fgxn gfxn neither non-zero or non-adjust. Either non-zero or non-adjust, then you can say that the pair of the two mappings is called non-compatible conditions. And additional is that f of x closure is contained in g of x. F of x bar is a subset of g of x, and satisfying the inequality, that means of d of fx gy less than or equal to 5 times of maximum of d of fx fy, d of gx dy, d of fx. Here it is, there is a some fx fy gx gy fy gx. This is a missed, this is a typographical mistake. The fy gx is also mentioned, and fy gy fy fx gy. This is I actually typographical mistake. Fx gy, this is highlighted part is the fx gy, d of fy gy and d of y of fy gx. And the pair is fg is satisfying the occasionally weakly compatible definition. Occasionally weakly compatible definition, then we can say that that is the f and g have a unique common fixed point in the x, and the fixed point of the fixed point is a point of discontinuity. Here it is, we are going to be show whether f and g both are common unique common fixed point. That point is a discontinuity f and g also. For showing of this, we need some very much in importance, that is the space is I'm taking the B metric space, and the conditions I'm going to be containment condition I'm taking, and the one of the definitions is that occasionally weakly compatible I'm taking this one. This much of I'm taking. So this proof is also very easy to show, but the last part is the very interesting. This is the last part is also very interesting proof also, very interesting proof. I would like to give this proof right now in this one, because it is useful to you, and further research those who wants to do research in the especially in this area, because in this area there is a several applications is possible, but right now it is a very difficult to find out the some applications also. At the end, I'm giving a some conclusions. In that conclusions also, I'm providing an some area of the applications also. Still, I'm also suffering. I'm also struggling to get the solutions in the especially in the applications area. I would like to go for the proof about this one because it is important about the proof, how to prove that fixed point is a point of discontinuity of both mappings. So first of all, I would like to give this is the proof non-compatibility. Non-compatibility already I explained it in earlier, and it is also mentioned. Non-compatibility of f and g implies that there exists a sequence in x and x such that fxn gxn tends to t as n tends to infinity for some t in x. And also the containment conditions also is one of the hypotheses in our main theorem. Fx bar is a gx. There is a point in u in x such that t is equal to g. The t equal to gu. T equal to gu, therefore we can write it that limit point is equal to t equal to gu. And now we have to show that whether fu equal to gu or not. So here it is, the problem is that the coincidence point we are going to be show that is the fixed point. So this is the suppose fu equal to, suppose if you are taking in fu equal to gu and we are with using of the main condition means that this is the one if we are using these if you are applying an x is equal to and y equal to xn in main condition, applying the limits, you will get it the proof easily. This is the generally traditional way to find out the answer. So therefore only for understanding purpose I'm giving this one is in the proof is also here. Let us take it x is equal to u and y is equal to xn in this inequality. After applying this one, that inequality is reduced in this format. What is this? This is the fu is equal to fu fxn and the phi of maximum of d of fu fxn, d of gu gxn and the fu gu, and applying of this one after reducing. And also I forgot to explain the verify in the main theorem. I forgot, actually it was mentioned in the first theorem. In the first theorem I mentioned what is the phi. Phi is a mapping from the r plus to r plus and is satisfying the phi t less than t for all t positive. I mentioned it earlier, therefore I'm not repeating the definition of a phi in every theorem statement. So therefore, with using of that condition phi of t less than t, and it is the contradictory part, therefore you can say that f equal to g. Now, once f is equal to u, then fu is equal to gu, then we are applying whether it is a fixed point or not. So therefore, we are going to be, since already it is one of the hypotheses in the main theorem, f of g is a OWC. OWC means that is the occasionally weakly compatible. Therefore, occasionally weakly compatible is not a weakly compatible, is not a compatibility. Therefore, I'm taking the benefit of occasionally weakly compatible. Then we get it. What is the occasionally weakly compatible definition? That is the pair fg is called occasionally weakly compatible, means that is the what is that, commute at their sum of the coincidence points, not for all, sum of the coincidence points. Therefore, I would like to take it fu equal to gu. If you mentioned the answer is t, then we are going to be ft. That means t means that ffu, and fgu, it is a coincidence commuting, and ggu and gt. Therefore, conclusion what happens? This is ft is equal to gt. Ft is equal to gt. Finally, what happens? This is ft is equal to gt. That ft is equal to gt. If we proved that ft is equal to t, automatically t is equal to ft is equal to gt, t is a fixed point. So it is very easy to identify the finally what we are going to be show, whether it is a t is a fixed point of f and g. Whether it is a t is a fixed point of f and g or not, we are going to be show. So it is very easy with using of the provided condition one. Applying the x is equal to t and y is equal to xn in the provided inequality. In this inequality, therefore we will get it that is easily. I'm not giving a proof solution. Easily we will be get it with using of the phi definition, phi controlling function phi, and applying the contradict. We will get a contradict ft equal to t. Once ft is equal to t, therefore ft is equal to t is equal to ft, that is equal to t. T is a fixed point. This is the general way. In a fixed point there in the olden tradition model, tradition method, it is a general way to show. So now this is the very beauty of the part of this one. This is the but every theorem is not possible to show that f is a discontinuous at a fixed point. It is a way we has to verify and each and every inequality. That means in particularly if we change of any relations, this one also I'm not getting the proof also. Some of the open questions also I posed in my paper, and also if your relation, that means if you taking the fx gy in place of fx gy fx fy, if you are writing, then right hand side if you are taking, left hand side if you are taking that one, you are not getting a fixed point. There we are not getting some relations. So this is now come to the conclusion. Now we have to show that the important part that f and g are discontinuous at a common fixed point t is equal to fu is equal to g. That means that is equal to fu. Suppose let us take it f is a continuous. Suppose f is a continuous. What happens if f is continuous? Already in the first page of the proof, what is the first page of proof? Fgxn is tends to t. If f is continuous, fxn is tends to ft. Therefore, I am using that. This is what happens. Limit n tends to infinity. Fxn is ft because f is a continuous. Fxn is also already tends to t. It is mentioned in the above non-compatibility definition. Ft already ft is already mentioned. It is a ft. It is a typography mistake. This is ft dt. And also that we can write it fgxn. What is the fgxn rule? That means this is f is continuous, and gxn is also tends to t. Therefore, this is ft. This is t. Therefore, if we are going to be mentioned f is continuous, that means limit n tends to infinity ffxn, limit n tends to infinity fgxn is converges to t. That is, we concluded that. Now I would like to find out what happens in d of t fgxn tends to 0 or not. Whether it is a d of fgxn tends to 0 or not. Next one. So suppose if it is not happens. Suppose if it is not happens, let us consider x is equal to xn, y is equal to fxn in the provided inequality. We can apply that fxn and g fxn, and applying these two conditions in the provided content and applying as n tends to 0, and we are going to be get it, that is equal to, we conclude that d of fgxn, g of xn is tends to 0. D of fxn tends to 0. That means that d of fxn, fgxn, g of fxn, gfxn is tends to 0. In fact, if it holds, definitely the pair fg is a compatible. But in our hypothesis, fg is not satisfying the compatibility condition. Therefore, this is a contradict. Definitely, it cannot be holds, it tends to 0. Because in our hypothesis, d of fgxn, gfxn either non-zero or non-adjust. But you got it. This is d of fgxn, g of fxn tends to 0. From our hypothesis is that f is continuous at a point t. At a fixed point t, if you are taking the continuous, you are getting it is we are getting it. This is converges to 0. So therefore, but in our hypothesis it is not happens. Therefore, our hypothesis is wrong. What is our hypothesis? F is continuous at t, at fixed point. Therefore, that is hypothesis wrong. Therefore, F is a discontinuous at the fixed point. In the same similar way, if you are applying the same conditions, then automatically G is also discontinued at the fixed point. This is the conclusion of the final part. This is part. So,
अभी तो
provided
बताई तो तेरे को
provided definitions and apply your
तब
area.
तब तो टिक करते ना तो और
And
मैं पैदल आती क्या फायदा
after that also several recently published some papers, they used a recent inequality. They are going to be published in this conditions. In as originally in the RP Pant used in place of occasionally compatible, he used in place of OWC. In place of OWC, he used R commuting. R commuting he used and he proved it in the and proved it and published in Journal of Mathematical Analysis Applications. I generalized that results, and this one is also this one. This is the main result of my talk. And after that, there is I would like to give a conclusion of this talk also. That is the applications conclusions. And I found some models also. I'm trying to getting a solutions in this area. I'm not get the conclusions in this results. In this, actually, I used this result. So we mentioned briefly a typical situation where our main theorem can be applied. Becker's-Pitts model is a frequently used in the biology and artificial intelligence. In this model, compensated type algorithms for neural nets and the neural nets are expected to reduce each neuron's deviation from its long-term equilibrium state. And such metabolic equilibrium can be described as a fixed points. A jump in the biological operations like the threshold frequency leads built into discontinuity of all other derived functions. Thus, our main result is applicable neural nets in the under suitable conditions also. Now, still I'm working in this area. In one of my student is also working in this area. I'm trying to get a results. Actually, I got it the theoretical results, but I'm going to be get it this theoretical results. There is some one of the papers, one of the some I would like to show. This is the I found it one recently neural networks discontinuity points results also. And those who are interested this paper, you can read it also. This is the conclusions of my I would like to show. First of all, applications in neural nets. Neural nets is the first application is published in earlier. I'm trying to generalize of this one. Becker's-Pitts model of neural nets. Discontinuity with using or discontinuity. I'm finding some models also in this area, neural nets and some other conditions. Equilibrium process vectors. In this condition also some applications is possible. I'm facing a struggle to finding some problems also. Finally, there I found it these mean value theorems and discontinuity functions also. Especially in the in this area, I'm finding some applications. This one. Now come to my few seconds, please. This is my conclusion of today's talk, but I'm not given the proof also. Same thing is also given because two mappings I provided a proof, therefore I skipped it to this one. Theorem 1 proof I mentioned it. I would like to show also within few seconds. Finally, that will also I'm going to be show. Then it will be conclude. This is my main result. Is it shared? Okay, this is the main result. In this conditions, also same part. I'm using a big complete metric space. The same result is also with using of the Picard iteration I'm completing, and this is the simplifications. I used it the simplification d of x1 decreasing sequence. I'm showing the general traditional way, and after getting the general traditional way, I'm going to be show that whether it is a Cauchy or not, and converges to 0 or not. Then finally, with using of the mere killer condition, I'm going to be showing that whether it is a Cauchy or not. With using of this Cauchy, and this is the final part. Since x is a complete, there is just a z in x, xn tends to z. T is I'm taking a weakly arbitrarily continuous. For two mappings, I'm taking the OWC and non-compatible T conditions. For two mappings, I'm taking the OWC and non-compatibility condition. In single mapping, I'm taking only T weakly arbitrarily continuous. I'm applying the T arbitrarily continuous and conclude that this is not a continuous at a fixed point of T. This is a glance look of the my first theorem proof. And also I forgot to give one important example. This is the example, this one. Let x is equal to 0 to 2 be the set of d of xy is equal to minimum of x plus y comma 2 if x is different from y, and this is the 0 if x is equal to 0. Especially this example, if t defined like this, especially this is defined, this is the B metric space, but not is a complete metric space. This is the conclusion of this one, and this is now it is. I would like to, what is that? I would like to open my present talk, this one. Now, I would like to invite to the all queries, those who have a queries. I would like to conclusion of this talk. I'm open for the question hour. Those who have a doubts and the clarification, I'm ready to explain. Yes.
Participants, the sir is ready to answer questions. Please ask one by one.
Like to close the camera. Okay. Okay, sir. Okay, clear now. It is now clear. Is this my voice is audible, sir?
Yes, sir.
Okay, sir. Please. Dear participants, please ask your queries. I'm trying to explain and clarifying your doubts. Anyone?
Please unmute your mic and ask the question, sir.
Please unmute your, those who wants to ask, please unmute your mic and you can ask. According to my sir, please loud clearly, please, my dear student, my dear participant, please, and ask me.
Hello, sir. Good evening.
Sir, very good evening. Please.
Sir, the session was very nice. We got very innovative ideas that we can use functional analysis. We are looking forward to use these ideas in linear algebraic manner. So I don't have any doubt, but thank you so much, sir, for the wonderful session, sir. Thank you.
Thank you very much.
Thank you, Patil ji.
This regard, I would like to give a one information also. With using of the C star algebra, they are also used the same technique also. They are also finding a fixed points with the, especially for the discontinuity mappings also. I found a one or two one paper is also recently, but they are used as C-star algebra. But I'm not working in the C-star algebra. Okay, thank you. Anyhow, thank you
Okay,
very
sir.
much.
Thank you, sir. Thank you.
Okay, sir, we will stop here and anyone?
Because of because of our participants only, I conclude as early as, because some maybe they may ask some questions. That's why I concluded fastly, at least 20 minutes before. Mhm.
Okay, sir, they don't have any questions.
Okay, nice, very good.
Thank you, sir, for your lecture on a problem of discontinuity at the fixed point. Thank you, one and all, for your good response and valuable support. Expecting the same cooperation for the remaining sessions also. Today's session concludes with vote of thanks by co-convener Dr. T. Srinivasarao Garu.
Good evening to all. On behalf of the Department of Mathematics and
Hello? Voice is not reached.
good evening to all.
Please, okay.
On behalf of the Department of Mathematics and the participants, I would like to express my heartfelt thanks to our today's resource person, Dr. KNVV Varaprasad Garu, who gave such a good and informative presentation on the problem of discontinuity at a fixed point. Fixed point theorems for discontinuous mappings have found various applications in communication engineering, neural networks, genetics, testing of algorithms, etc. It is a very active area of research going on now. Despite his busy work schedule in the university, Sir cordially accepted our invitation immediately and gave a talk in today's session. Thank you very much, sir, for giving such a wonderful presentation. Thank you, sir.
Thank you very much, sir, one and all. And once again, thank you very much for giving this opportunity from the Department of Mathematics, Capital Engineering College. And hands up that your management also, thanks to your great management for giving this opportunity, accepting my presence also. And also they're providing a I mean, directly or indirectly, technical peoples in our teaching faculty, everyone is also supporting to me time to time, and they are following up also, and also they providing every information time to time also with a very good patience. Once again, I would like to thanks to each one and all also. Thank you very much, sir.
Thank you, sir.
Thank you.
For your kind words.
Thank you, sir.
Participants posted feedback link in the WhatsApp group, YouTube live link, and Q&A question box. It will be live for 1 hour. Later, it will be disabled. So today's session is over. You can leave the session now. Thank you.
Oh, sir, someone is raising hand. No.
అది అలాగే ఇందాక నుంచి అట్లాగే ఉంది సార్ అసలు.
Okay, sir. Sir, thank you very much. May I leave now?
Yes, sir. Thank you very much, sir.
Thank you very much. Meanwhile, if it is any needed, you can call also. I will come and join.
Definitely, sir. Definitely, sir.
Thank you very much.
Thank you very much, sir, for your
Thank you.
valuable lecture.
Thank you very much.
Participants, you can leave now. Today's session is over.
Thank you, sir.
Okay.
Thank you, sir.
Thank you.